Well, good afternoon, ladies and gentlemen. It's Monday, December 13th. I'm going to try to cover section 8.2, arithmetic sequences. Sorry for the inconvenience that the internet outage caused. Section 8.2 is entitled Arithmetic Sequences. And series. First of all, a definition of an arithmetic sequence. The first term of an arithmetic sequence denoted as a sub 1. To get to the second term of an arithmetic sequence, you have to add what's called a common difference. To get to the third term of a arithmetic sequence, you have to add the common difference to the second term. Fourth term is obtained by taking the third term and adding this common difference, etc., etc. Oops, these should be commas here. So a sub 1 is the first term. And to get to the second term, we take the first term and add the common difference to it. To get to the third term, we take the second term and add the common difference to it. But our second term is the first term plus the common difference. So we can take this and substitute in for a second term here, in which case we have our first term plus the common difference plus another common difference, which simplifies to our first term plus 2 times the common difference. Our fourth term is obtained by taking the third term and adding to it the common difference. But the third term is this right here. So this can get substituted in for your third term here. So this is going to be your first term plus 2 times your common difference plus another common difference gives you your first term plus 3 times your common difference. Your fifth term is your fourth term plus, again, that common difference. But your fourth term is this. So this can substitute in place of your fourth term. So we have our first term plus 3 times our common difference plus a common difference gives you our first term plus 4 times a common difference. If we continue in this fashion here, we can derive what's called an nth rule for an arithmetic sequence. You can see that the factor in front of the common difference lags 1 behind the index of the term. So our third term, we have 2 in front of the common difference, fourth term, 3 in front of the common difference, fifth term, 4 in front of the common difference. So in general, our nth term of an arithmetic sequence is found by taking the first term and adding to it n minus 1 times your common difference. This, ladies and gentlemen, is called the nth rule for an arithmetic sequence. So this is a very important formula to have memorized, where again, a sub 1 is the first term of the arithmetic sequence. D is called the common difference. Where D where D is actually the next term of an arithmetic sequence, subtracting the previous term. And this leads us to what's called a recursive definition for an arithmetic sequence, to say that the next term of an arithmetic sequence is really your previous term plus a common difference. So this is called a recursive definition for an arithmetic sequence. And this is valid for n greater than or equal to 1. Okay. So we see that we have an nth rule, and we also have a recursive rule for an arithmetic sequence here. So it's very important to have this nth rule when working with arithmetic sequences. And again, arithmetic sequence is a sequence whereby to go from one term to the next term, you add what's called a common difference. All right, I'm going to give ourselves some sequences to look at, and I'm going to ask ourselves this question: which of the following are arithmetic sequences? The first one we'll look at has the terms of 15, 19, 23, 27, etc. So this is an infinite sequence. Is this sequence arithmetic? Well, if there's a common difference, then it is arithmetic. So if we take 19 minus 15, we get 4. If we take 23 minus 19, do we still get 4? The answer is yes. 27 minus 23, do we get 4? Yes. So it appears that this is an arithmetic sequence where the common difference is 4. So this is an example of an infinite arithmetic sequence. Another sequence would be 8, 0, negative 8, negative 16. Is this sequence arithmetic? Well, to be so, it has to have a common difference. So 0 minus 8, is that equal to negative 8 minus 0? Is that equal to negative 16 minus a negative 8? Is that true? Well, 0 minus 8 is negative 8. Negative 8 minus 0 is negative 8. Negative 16 minus a negative 8 is negative 16 plus 8, which is negative 8. So it does appear that this is an arithmetic sequence where the common difference is equal to negative 8. So this would be arithmetic. Here's another infinite sequence. Is this infinite sequence arithmetic? Well, 4 minus 2 is equal to 2. 8 minus 4, however, is equal to 4. And 16 minus 8 is equal to 8. And so, ladies and gentlemen, there is no common difference between successive terms of this sequence. And so this sequence is not arithmetic. Not arithmetic. Okay. How about this sequence here? All right, let's see if this has a common difference. If you take 15 fourths and you subtract off 3 over 1, that's really 15 fourths minus 12 fourths, which is 3 fourths. But is that the same thing as 9 halves minus 15 fourths? You've taken 9 halves, subtract off 15 fourths. Do we get this 3 fourths? Well, common denominator is 4, multiplying this fraction by 2 over 2, building it up to 18 over 4, minus 15 fourths. It appears that we do get that 3 fourths. Is 21 fourths now minus 9 halves? Does this give us that common difference of 3 fourths? Common denominator is 4, so 21 fourths minus this fraction gets multiplied by 2 over 2 to build it up to an equivalent fraction of 18/4. And 21 minus 18 is 3, so we get 3/4. Yes, ladies and gentlemen, it does appear that our common difference for this sequence is 3/4. So this would be an arithmetic sequence. And it would be an infinite arithmetic sequence. So again, arithmetic sequences must have a common difference. If the sequence does not possess a common difference, then the sequence is not arithmetic. All right, suppose we want to write the first 5 terms of the arithmetic sequence where the first term is equal to -5 and the common difference d is equal to 4. All right, well, the first term of this arithmetic sequence is going to be -5. The second term of this arithmetic sequence, denoted as a sub 2, is going to be our first term plus the common difference. So it's going to be -5 plus 4, which is going to be -1. Our third term is going to be the second term plus our common difference, which is to say, however, our second term is -1. So it's going to be -1 plus our common difference of 4. So our third term will be 3. Our fourth term is going to be the third term plus the common difference. But our third term was 3, so we'll have 3 plus the common difference of 4. So our fourth term would be 7. Our fifth term is going to be the fourth term plus the common difference. But the fourth term was 7. And 7 plus 4 gives us 11 for the fifth term. And we could go on and on and on. So the first 5 terms of this arithmetic sequence are -5, -1, 3, 7, and 11. Those are the first 5 terms of this arithmetic sequence. All right. This next problem here, suppose we want to find the 9th term of the arithmetic sequence. Where the first term is -4 and the 22nd term of the sequence is equal to 164. In other words, ladies and gentlemen, we want to find the 9th term. We want to find a sub 9. Well, using our nth rule that we developed several pages back, which says that your nth term in general is equal to your first term plus n minus 1 times your common difference. And knowing our first term is -4 and our 22nd term is 164, we can find our common difference here by using this nth rule here. So using the nth rule, I'm going to say my 22nd term is equal to my first term plus n is 22. So 22 minus 1 times our common difference. But ladies and gentlemen, our 22nd term, they gave it to us. It's 164. So 164 is equal to our first term, which is -4, plus 22 minus 1 times the common difference. We just have to solve this equation for d, the common difference. So this is 164 is equal to -4 22 minus 1 is 21, so plus 21 times d. We have to solve for the common difference d. Adding 4 to both sides of this equation, we get 168 is equal to 21d. Divide both sides by 21, and we find our common difference is going to be 8. So now we know our common difference for this arithmetic sequence is 8, and therefore we can easily find the 9th term of this arithmetic sequence to answer this question. Okay, so now to find the 9th term, we use our nth rule again, trying to find the 9th term, which is going to be equal to our first term, plus n is now 9, so 9 minus 1 times our common difference. Our 9th term, therefore, of this arithmetic sequence is going to be our first term, which was given to us as -4, plus 9 minus 8, 1 is 8, times our common difference, which we found to be 8. Hence, our 9th term of this arithmetic sequence is going to be -4 plus 64, or is going to be 60. And so, therefore, we are done with this problem. We have determined our 9th term, which is 60. All right, this next one has us trying to find the number of terms that are in the arithmetic sequence. And here is the arithmetic sequence that they give us. 8, 14, 20, 26. On and on this goes up to some other entry, 320. Okay. So they want us to find the number of terms that are in this arithmetic sequence. It is a finite arithmetic sequence. So we have to find what term number this is here. I mean, is this the 20th term, the 30th term, the 40th term? We don't know. We know that 8 is our first term. We know in general this is our nth term here. We got to find what n is here to determine what term that 320 is in this arithmetic sequence. All right. Well, it is an arithmetic sequence, so we know it possesses a common difference. And therefore, our common difference has to be equal to 14 minus 8, or it has to be 20 minus 14, or it has to be 26 minus 20, etc., etc. So as it turns out, our common difference is going to be 6. So now we know our common difference is 6. We know our first term is 8. Therefore, using our nth rule for an arithmetic sequence, and our nth rule is this rule here, where your general nth term can be found by taking your first term and adding it to n minus 1 times your common difference. Now we know this is our nth term, which is 320, so we'll replace a sub n with 320, replace our first term with 8, and we don't know what n is, we don't know what term this is, so we'll leave n as n. We know our common difference of 6, and now we have to solve this equation for n here to determine what term number this 320 is in this arithmetic sequence. And that will enable us to determine how many terms are in this arithmetic sequence, which is a finite arithmetic sequence here. Okay, this is a finite sequence. Well, solving for n, we could subtract 8 from both sides. We'll have 312 is equal to, distributing the 6 inside the parentheses here, equal to 6n minus 6. Solving for n now. After distributing the 6, subtracting 8 from both sides, we now add 6 to both sides. So we have 318 is equal to 6n. Dividing both sides by 6, we determine what n is equal to. So as it turns out, n is going to be equal to 53. And so, ladies and gentlemen, as it turns out, there are 53 terms in this sequence. And as it turns out, our 53rd term of the sequence is 320. So there are 53 terms in this arithmetic sequence, and we have answered that question. All right, let's try this next problem here. Given two terms of an arithmetic sequence, and the two terms that we are given are the 15th term, which is 86, and the 34th term of the sequence, which is 200. They want us then to find the 150th term of this arithmetic sequence. Well, what do we know? Using the fact that our 15th term is 86 and our nth term rule, which is this for an arithmetic sequence, we have our 15th term is going to be equal to our first term plus n is 15, so 15 goes in for n here, so that'd be plus 15 minus 1 times our common difference, which we don't know. We don't know our common difference. So we don't know our first term and we don't know our common difference. But we do know our 15th term is 86, so I can put 86 in for our 15th term. And as it turns out here, we have an equation and two unknowns. And the two unknowns are our first term of this arithmetic sequence and the common difference. I'm going to put a box around this equation. We're going to have to visit this equation later on. Now, using the fact that our 34th term is 200 for this arithmetic sequence and using the nth rule again, I can say my 34th term is equal to my first term plus n is 34 now in my nth rule. So I put 34 in for n here. So we'll have 34 minus 1 times your common difference. We know our 34th term is 200 though. So 200 is equal to our first term plus 33d. And now, ladies and gentlemen, we have another equation and two unknowns, namely the first term of our sequence and the common difference. We can now solve this system of two linear equations and two unknowns to find the first term in our sequence and also the common difference. Once we determine those, we will then be able to find the 150th term of our arithmetic sequence. So what we're going to do is we're going to pair together these two equations. This first one is a sub 1 plus 14d is equal to 86. Underneath this one, I slide the second one, which is to say the first term plus 33d equals 200. In order to solve this system, I will use the elimination method, and I will choose to eliminate the variable a sub 1. To do that, I'm going to multiply my first equation by a negative 1, and I'm going to obtain an equivalent first equation, which is going to be negative 1a sub 1 minus 14d equals negative 86. The second equation slides underneath this equation. And now when we add these equations together, you can see that a sub 1 drops out, cancels out. The d terms add up to what? Well, 33 minus 14. Adds up to 19. So we have 19d. And 200 minus 86 is going to be 174. Wait a minute, is that right? 200 minus 86. It's going to be 114. This is 114. Sorry about that. All right, so we have this equation, 19d is equal to 114, divide by 19, and d is going to be equal to, as it turns out, 6. So now we know our common difference, d is equal to 6. To find our first term of the sequence, we choose one of these equations here. I will use this one here, the original first one. I will replace the common difference with 6. And then I will solve for the first term. So a sub 1 plus 84 is equal to 86. Subtract 84 from both sides, and we get our first term is 82. Is going to be 2 rather. Our first term is equal to 2. All right, so now we know the first term of our arithmetic sequence. We know its common difference. We should be able to use that now to determine the 150th term for this sequence. And so to find the 150th term of this sequence, we're going to use our nth rule again. And we want to find the 150th term, which is going to be equal to the first term plus n minus 1, where n is 150, times our common difference. So our 150th term is going to be equal to our first term. But we found our first term back over here was equal to what? 2. 150 minus 1 is 149 times the common difference. But we determined our common difference back here was 6. So now we can just solve for our 150th term of this arithmetic sequence. So we're going to have 2 plus, and 6 times 149 is going to be, let's see, 54, 24, 29, 894. And 894 plus 2 is 896. And so, ladies and gentlemen, the 150th term of this arithmetic sequence turns out to be 896. Okay, now we're going to start looking at series associated with an arithmetic sequence. Consider the finite arithmetic sequence. The nth partial sum of this sequence is the sum of the first n terms of the sequence. So the first partial sum is the sum of just the first term in the sequence, which is 1. The second partial sum is the sum of the first 2 terms of the sequence, which is to say 1 plus 4 or is 5. The third partial sum is the sum of the first 3 terms of the sequence, which is to say 1 plus 4 plus 7, which is going to be 12. The fourth partial sum of this sequence is going to be the sum of the first 4 terms. Or notice, ladies and gentlemen, is going to be the third partial sum, that's what this is, plus the 4th term of the sequence. Well, the third partial sum was 12, and the fourth term of this sequence is going to be 10. So the fourth partial sum, as it turns out, is going to be 22. The fifth partial sum, which is the sum of the first 5 terms of this sequence, is really the fourth partial sum, which is the sum of the first 4 terms, plus the fifth term. But the fourth partial sum was found to be 22. So 22 plus the fifth term of 13 nets us with the fifth partial sum, which is 35. There's an interesting note here surrounding this problem. Suppose I take the fifth partial sum of this sequence in ascending order, which is to say the sum of the first 5 terms, 1 plus 4 plus 7 plus 10 plus 13. What if I take the fifth partial sum of this sequence where the terms are now added in the reverse order? 13 plus 10 plus 7 plus 4 plus 1. So the fifth partial sum in ascending order, the fifth partial sum in descending order. Notice if I add these together here, one partial sum of the first 5 terms plus another s of 5 is going to give you 2 times s of 5. If I add the right side of these equations together, notice these add up to 14. Every one adds up to 14. 14 plus 14 plus 14 plus 14 plus 14, which is implying that 2 times your fifth partial sum is really 5 times 14. Which is really implying that your fifth partial sum, when we divide both sides of this equation by 2, is really 5 times 14 divided by 2. Which, notice, does give you 35. Interesting to note that. We can use this interesting fact surrounding this finite arithmetic series to generalize the sum of the first n terms of any arithmetic series. So, using this interesting fact and generalizing, if I take the nth partial sum of an arithmetic sequence, in general, that'll be the first term added to the first term plus the common difference, which is the second term, added to the third term, which is the first term plus 2 times your common difference, added to the fourth term, which is your first term plus 3 times your common difference, added to, on and on this goes, up to your nth term of your sequence. If I write this partial sum in ascending order and then turn around and write it in descending order, and suppose I then add these together. If I add the left side of my equation together, I'll have 2 times the nth partial sum. And if I add these together, corresponding terms on the right side together, I'll have my first term plus my nth term, I add these together, but notice the d's will add up to 0. They cancel out, leaving me with the sum of the first and the nth term. Adding these terms together, notice the two d's cancel out or add up to 0, leaving me with the sum of the first term and the nth term. Adding these corresponding terms together, the three d's cancel out, leaving me with the sum of the first term and the nth term. In fact, this is going to be the case, for the remainder of this series here. And the sum of the last terms here is going to be the sum of the first term and the nth term. And now, ladies and gentlemen, if I realize that on the right side here, we have the sum of the first term and the nth term written n times. But when you add a number together to itself n times, that's equivalent to multiplying that number by n. So therefore, 2 times our nth partial sum is going to be 2 times the sum of the first term and the nth term. Not 2 times, n times, excuse me. There should be an n here, because we're adding the sum of the first and the nth term together n times. So repeated addition is basically more conveniently represented as multiplication. So this should be n. But then if I solve for my nth partial sum by dividing both sides of my equation by 2, what I've developed here is an interesting little formula here. So the sum of the first n terms of any arithmetic sequence is always going to be equal to the number of terms we're adding up divided by 2 times the sum of the first and the last term that we're adding up. A very important formula here. This is called the nth partial sum formula for an arithmetic sequence, which will give us the sum of the first n terms of an arithmetic sequence. We can put this formula to use here in this next example. It says find the sum of the first 100 terms of the following arithmetic sequence: 8, 12, 16, 20, 24, 28. We know our first term of this sequence is 8. We know the common difference is 12 minus 8, or 16 minus 12, or 20 minus 16, etc., is equal to 4. So therefore, ladies and gentlemen, we know the first term of the sequence is 8. We know the common difference is 4. To find the sum of the first 100 terms of this arithmetic sequence, we can use our formula we developed here. So the sum of the first 100 terms, where n is 100, is going to be equal to 100 divided by 2 times your first term. First term is 8 plus our 100th term. Now, we don't know what our 100th term is for this arithmetic sequence, but we can find it by using our nth rule. So therefore, using our nth rule, we can find our 100th term to be equal to our first term plus n minus 1, where n is 100, so 100 minus 1 times our common difference. So our 100th term is going to be our first term, which is 8, plus 100 minus 1, or 99, times the common difference being 4. And therefore, our 100th term, when we work this out, is going to be 404. So now, ladies and gentlemen, we know our 100th term. So therefore, the sum of the first 100 terms of this arithmetic sequence is going to be 100 over 2, which is going to be 50, times our first term, which is 8, plus our 100th term, which was found to be 404. So we're really going to have 50 times 412, and that gives us the sum of the first 100 terms of this arithmetic sequence is going to be 20,600. And there's your answer. There's the sum of the first 100 terms of this arithmetic sequence here. Suppose you want to find the sum of the finite arithmetic series given to us in the form of summation notation, where k is the index of summation and it runs from 1 to 70. And the nth rule of this sequence would be 3k plus 5. Well, if we list the first couple of terms of this sequence, when k is equal to 1, we put 1 in for k. The first term of this sequence, therefore, would be, or this series, would be 3 times 1 plus 5 plus, and then we let k increment to 2, and we put 2 in for k. The second term of this series would be 3 times 2 plus 5. Plus, then we let k increment to 3. We put 3 in for k. So the third term of this series would be 3 times 3 plus 5. Plus dot, dot, dot. This goes on forever. Okay. Well, this is going to be equal to the first term of our series, which is going to be 8, added to the second term of our series, which is going to be 11, plus the third term of our series, which is going to be 14, plus on and on this goes. Now, this would take a long time if we were to add the first 70 terms of this series together by running k from 1 to 70. That would take a tremendous amount of time. But an easier way to go is to realize that the first term of the associated arithmetic sequence is going to be 8. And we know the common difference of this arithmetic sequence is 11 minus 8, which is equal to 3, or 14 minus 11, which is 3. And then, ladies and gentlemen, we can use our nth partial sum formula that we developed earlier. So to find the sum of the first 70 terms of this arithmetic series here, that's what this is saying, we let n be 70. So therefore, the sum of the first 70 terms in this arithmetic sequence is going to be 70 divided by 2 times the first term plus the 70th term. Now, we know the first term of this sequence, but we don't know the 70th term. Well, to find the 70th term, we can use our nth rule. So the 70th term is going to be equal to our first term plus n minus 1, where n is 70, times our common difference. So the 70th term of this arithmetic sequence is going to be equal to our first term, which is 8, plus 70 minus 1 is 69, times our common difference, which is 3. So, as it turns out, our 70th term here is going to be 215. So therefore, the sum of the first 70 terms of this arithmetic sequence is going to be 70 divided by 2 times your first term, which is 8, plus your 70th term, which is 215. That's going to be equal to 35. 70 divided by 2 is 35, times 8 plus 215 is 223, and the sum works out to be 7,805. That's the sum of the first 70 terms of that arithmetic sequence there. All right, arithmetic sequences can be applied to the real world. This is problem number 67 on page 710. Suppose we go up on a tall building, ladies and gentlemen, and we drop maybe like a stone. We just drop it from the tall building. After the first second, the stone will have dropped 16 feet. This is after 1 second. After 2 seconds, the stone will have dropped 48 feet. That's during the second second. During the third second, the stone drops an additional 80 feet. This is during the third second, etc., etc. Okay. So what we have here, as far as the distances covered by this stone per second as it's dropped from the top of this building here, we have a sequence, ladies and gentlemen. The first term of which is 16 feet, the second term of which is 48 feet, the third term of which is 80 feet, etc., etc. Now, they want us to develop an nth rule for this arithmetic sequence here. Well, the first term is 16, actually 16 feet. The common difference here is the difference between successive terms. So 48 feet minus 16 feet, or the common difference could be found by taking 80 feet and minusing off 48 feet. At any rate, the common difference works out to be 32 feet. Okay. All right, so therefore, using our nth rule, which is this rule we developed a ways back, we can write our nth term or nth term rule for this arithmetic sequence. So the nth term, or the amount of feet that the rock drops during the nth second, if you will, is going to be equal to the first term, which is 16 feet, plus n minus 1 times your common difference, which is 32 feet. Distributing the 32 feet inside the parentheses here, we have a sub n is equal to 16 feet plus 32n feet minus 32 feet. Okay. Combining like terms, 16 feet minus 32 feet. Therefore, a sub n is equal to 32n minus 16, and that would be feet. So, ladies and gentlemen, the nice thing about this nth rule for this arithmetic sequence, we could use this nth rule to determine how far a rock drops during any second. Okay, during any second. For instance, during the first second, we let n be 1. And the distance the rock will have fallen during the first second is, using our nth rule, replacing n with 1, is going to be 32. 32 times 1 minus 16 is 16 feet. During the second second, how far did the rock fall? Well, we let n be 2 in our nth rule, so a sub 2 is equal to 32 times 2 minus 16, which means our rock will have dropped 48 feet during the second second. They want to know how far our rock will drop during the 8th second. So we just let n be 8 in our nth rule that we developed here. And therefore, 32 times 8 minus 16. So the rock will have dropped how far during the 8th second? Well, that's going to be 32 times 8 minus 16, which is 256 minus 16, or 240 feet. And they also want us to find the total distance that this rock will have falling during the first 8 seconds after it's dropped. To find that, ladies and gentlemen, we use our nth partial sum formula. So we want the total distance the rock will have fallen during the first 8 seconds after being released from the top of this building. N is going to be 8, so that's going to be equal to 8 divided by 2 times your first term plus your 8th term of this sequence. So that's going to be 8 divided by 2, which is 4, times your first term is 16 feet, plus your 8th term of this sequence is 240 feet. Hence, it looks like this rock will have dropped 4 times 256 feet, which is to say 1,024 feet. And therefore, this rock will have dropped a total distance of 1,024 feet, 8 seconds, during the first 8 seconds after it's released from the top of this building. The rock will have covered this distance, 1,024 feet. So that's just one area that gives you an idea as to where arithmetic sequences can be used. I will update the homework on ALEKS for section 8.2 involving arithmetic sequences.